As incredible as it may seem, there will come a time when we will live in other worlds, both on the Moon, on Mars, and in the space between them. And when that day comes, just as it has always happened, our children will look with curiosity towards these new horizons, with a desire to go further and explore what lies beyond. However, beyond Mars, the distances between worlds grow immensely, even within our own solar system, truly becoming vast among the stars. If we want to reach these distances, we will need to learn how to go fast. With our current knowledge of physics and engineering, we could create nuclear-powered spacecraft to take humans to all the worlds in our solar system. However, a nuclear-powered spacecraft bound for our nearest star, Proxima Centauri, would have to house hundreds of generations of people, all living their entire lives before reaching the destination, 4.2 light-years away. This spacecraft would take decades to reach the orbit of Saturn, and over 2,000 years to reach Proxima Centauri. This makes it clear that we need to be able to go faster, and that is exactly what an innovative project is seeking in this moment.
We need to be able to achieve higher speeds with our current knowledge of physics. However, to accomplish this, innovative engineering must be developed. We can envision a propulsion system with a sun as its heart, a fusion engine capable of accelerating a spacecraft to 5% of the speed of light. With such propulsion, this spacecraft could cross the orbit of Saturn in 6 months and reach Proxima Centauri in just over a century. However, if we aim to traverse interstellar distances within less than a human lifetime, the need is to go beyond, remarkably fast. The universe has shown us that this speed is possible by altering the scale of space itself. We are diligently working to develop new understandings of physics, seeking to comprehend how this can be controlled. If we can build a spacecraft with a propulsion system capable of contracting space ahead and expanding space behind, this spacecraft would have the potential to traverse enormous distances effectively, surpassing the speed of light. In such a scenario, this spacecraft could go from Mars to Saturn in a matter of minutes and reach Proxima Centauri in less than 6 months. From there are no limits to where we could go. Perhaps one day, humanity will gaze upon an alien night sky and strive to find the faint, yellow point that is our sun, our home. For the first time, we may realize that we are not alone in the universe.
Could this be the most effective way to reach regions in our cosmic neighborhood and beyond? Firstly, we need to grasp the idea and understand how we can harness it to our advantage. One of Einstein's greatest contributions was to show that space-time is not something fixed and unchangeable, but dynamic and flexible, susceptible to the influence of mass and energy. Mr. Einstein was brilliant. Gravity is the result of the deformation of space-time caused by massive bodies, such as planets and stars. The larger the mass of a body, the greater the curvature of space-time around it, and the stronger the gravitational force it exerts on other bodies. Space-folding would be a way to create a bubble around a spacecraft, doing exactly what a dense body does, contracting space-time in front of it and expanding it behind, creating a shortcut in space. This way, the spacecraft could move without accelerating or decelerating, merely altering the space-time around it. This would be a way to overcome the limitation of the speed of light, which is the maximum speed that anything can attain in space-time. The challenge we face in space is very similar to what we encounter when climbing up and down mountains here on Earth. Imagine you want to go from point A to point B in a mountainous region. You would have to spend a lot of time and energy climbing up and down the mountains, following the terrain's relief. In space, gravity is like the mountains, creating curvatures in space-time that hinder the movement of bodies. If we could bend space-time in a controlled manner, we could overcome these difficulties. Although this idea may seem like something out of science fiction, a part of this concept is already present in our lives, known as gravitational assist. This technique was initially proposed as a maneuver to be executed in the middle of a journey in 1961 by American aerospace engineer Michael Minovicci. The first practical application occurred in 1973 when the Mariner 10 probe was traveling towards Mercury and Venus. The probe used the gravity of Venus to approach Mercury. Since then, gravitational assist has been employed by various interplanetary probes. Before this discovery, reaching planets beyond Jupiter was impractical, as probes use the gravity of these planets to increase their speed and reach the more distant planets of the solar system, such as Uranus, Neptune, and Pluto. This technique provides fuel, time, and financial resource savings as the spacecraft utilizes the planet's gravity to gain or lose speed, which varies depending on the direction and angle of entry into a planet's orbit. Applying the same idea, Miguel Alcubierre suggested in 1994, creating a warp bubble using Einstein's general theory as a foundation. It is assumed that no body with mass can travel faster than light.
It is assumed that no body with mass can travel faster than light. However, you have created the Alcubierre formula, which somehow contradicts this assumption.
So, well, it's not exactly like that, but I don't call it the Alcubierre formula. Other people do.
Sencillito.
What I proposed was a simple model, a kind of instant passage, using Einstein's theory of space-time deformation. Normally, we cannot travel faster than light, but if we can deform space in the same way that gravity deforms the geometry of space, we could somehow surpass and travel faster than light.
How? How can we deform it?
Using the same theory of Einstein on the deformation of space-time, we can envision a deformation of the geometry of space that would somehow allow us to surpass and travel faster than light. Many have heard of the curvature of space that Einstein taught us, demonstrating how gravity is a curvature of the geometry of space. For example, when the Earth revolves around the Sun, we now understand that the Sun, with its massive mass, warps space, and the Earth, in trying to follow the straightest path possible, is forced to orbit around the Sun. Space can be curved and stretched, as seen in the expansion of the universe. When we talk about the origin of the universe and the Big Bang, we understand that the space between galaxies stretches three-dimensionally, as does time. The idea is to use these contractions and stretches of space to travel faster than light. The expansion of space behind us and the compression ahead would bring us closer to what is ahead and move us away from what is behind. Essentially, the idea is to expand the space behind us, stretching it greatly, and at the same time compress it in front. This would bring me closer to what is ahead and move me away from what is behind. In principle, this can be done for any distance and period.
So Alcubierre envisioned a way to harness this property by creating a warp bubble. This bubble would be a region of space-time isolated from the rest. Inside the bubble, the spacecraft would be at rest, without decelerating or accelerating. Outside the bubble, Space-time would be contracted in front of the spacecraft and expanded behind it, causing the spacecraft to continually fall toward this deformation. This way, the spacecraft could move at very high speeds without violating the laws of physics. Alcubierre's proposal, although based on Einstein's general relativity, faces many challenges to become a reality, with one of the main problems being the need for an enormous amount of energy to generate a warp bubble. According to Alcubierre's calculations, it would require an amount of energy equivalent to the mass of a planet like Jupiter to create a warp bubble sufficient for a small spacecraft. However, this amount of energy is much greater than what humanity currently possesses and would be impractical to obtain or store. Another problem is the instability of this bubble, which could rupture or collapse at any moment due to disturbances, jeopardizing the safety of the spacecraft and its passengers. In addition to the potential destructive nature due to the released energy, there are also unknown and potentially dangerous effects on the environment and passengers. The warp bubble could accumulate radiation and particles during the journey, releasing them violently upon dissipation, causing harm to space and nearby planets. There is also the question of how passengers would perceive and endure the journey, and how they could control and communicate with the spacecraft, as the warp bubble would isolate them from the rest of space-time. One possible solution to reduce the amount of energy needed to generate a warp bubble is proposed by Harold White, an American physicist, mechanical, and aerospace engineer, known for proposing new concepts of faster-than-light propulsion. He led NASA's Advanced Propulsion Physics Laboratory and suggests modifying the design of the Alcubierre bubble. White proposes using a ring shape instead of a sphere and concentrating the energy at a specific point. According to White's calculations, this approach could significantly reduce the amount of energy needed to create a warp bubble sufficient for a large spacecraft. This difference would be from a planet like Jupiter to an object like Voyager 1. Despite this significant reduction in energy, it still remains very high by current standards. The way Alcubierre found to generate all this amount of energy is through exotic matter, a hypothetical form of matter with unusual properties. However, the existence and nature of this matter are uncertain, and there is no evidence that it can be found or produced in nature or in the laboratory. Some researchers believe it may be related to dark energy and dark matter.
Doctor, estábamos hablando hace un momentito.
We were talking a bit about science fiction, and the advances in science aren't really showing us how far humans can go. However, it's also showing us its limitations, telling us what cannot be altered.
Le está mostrando sus limitaciones.
It's true, we are discovering how the universe is, and something I really like to say is that it is as it is, not as we would like it to be. We are trying to understand how the universe is, what things are possible, what can happen, and what cannot. That's part of what
Isso é
science
parte do
teaches
que a
us.
ciência nos ensina.
Sometimes
Às
it
vezes nos
disappoints us
desiludimos
because
porque
we would
gostaríamos que
like
algo
something to
acontecesse,
happen,
mas
but we
descobrimos
find
que não é
out it's
possível.
not
Por
possible.
exemplo,
For instance, we were discussing traveling faster than light, and perhaps that is impossible.
But you say it is possible in the world of mathematics.
Mathematically, it's possible, but not everything that's possible in mathematics occurs in reality. Mathematics is much richer than the real world. When people ask me what mathematics is, I believe that mathematics is the art of imagining possible worlds. It is always exploring all the possibilities allowed by logic. However, we live in a single world, and all this vast universe of mathematics that applies to the real world is much more restricted than the universe of mathematics that applies to truth.
Do mathematics always give us an answer?
Una solución.
No, not always, but they tell us what things are possible using the laws of logic.
¿Qué cosas son posibles usando las leyes de la lógica?
Mathematics is essentially pure logic applied to things that can be measured, like numbers, but it is pure logic. The laws of logic allow us to imagine things that may not exist, but they do not permit us to imagine anything that violates logic.
White also proposes the use of an electric field to alter the geometry of space-time, instead of relying on exotic matter.
The Alcubierre warp metric and other ones require exotic matter. How, and so I presume if you're trying to make some kind of Alcubierre thing on the optical bench with this interferometer, are you trying to make exotic matter in your test article, which you didn't say very much about?
Yeah,
Or
so
what's going on with that test article, and why should it be an Alcubierre-like effect?
So that test article is trying to establish more accurately the requirements as set up by the mathematics, working with negative vacuum energy, Casimir force.
White is currently involved in the EagleWorks project, which aims to test the feasibility of generating warp fields with smaller amounts of energy. These research efforts are still in the early stages, and there is no concrete evidence that it is possible or even practical. However, it represents a significant step forward in the quest for some form of faster-than-light travel. If someday we achieve this feat, it would be possible to travel to neighboring star systems, and even more distant ones in a much shorter time than it would take with conventional means limited by the speed of light. One of the most recent studies on warp propulsion was conducted by theoretical astrophysicists Alexei Bobrik and the young self-taught physicist Gianni Martire. They proposed a new class of solutions to Einstein's equations describing warp bubbles, and demonstrated that these bubbles could be constructed with finite amounts of common energy without violating the laws of physics. Furthermore, they suggested that these bubbles can be controlled by an observer inside the bubble and can assume different shapes and sizes.
Causality.
On the warp drive, how do you avoid causality violation, or does it happen?
You never locally exceed the speed of light, so you can't do any. I like Dr. Hugh as much as the next guy, but you can't. There's no time travel possible with a space warp.
And even in the worst-case scenario, where humans cannot be transported by this technology due to the hostility of space, it would be possible, at the very least, to send probes to explore planets that exhibit favorable conditions for life, expanding the horizons of our understanding of the place we live in.